Welcome to today's lesson on Paul Academy. In this video, we are going to talk about limiting reactants, which can also be referred to as limiting reagents. Along the way, we will also discuss a related topic called excess reactants, as well as percentage yield. Limiting and excess reactants and the percent yield all have to do with chemical reactions.
Up to this point, we've only done stoichiometry calculations. We were only given the amount of moles of one of the reagents. We are also assuming that both reagents completely use one another up in the reaction. However, this is usually not the case in most of the reactions that we see in our daily lives.
To explain it from the beginning, we actually don't want to start talking about the chemistry. Instead, we want to start talking about some analogies. When most of you were in elementary school, you probably bore witness to the greatest scientific experiment ever, the classic baking soda and vinegar erupting volcano. In general, you'd have a bottle of vinegar, but only a few tablespoons of baking soda. Eventually, you'd get to the point where no matter how much acetic acid, also referred to as vinegar, you placed inside of the volcano, nothing would happen, because the baking soda was all used up. Now, why is that? This can be explained by the concept of limiting reagent and excess reagent. Now let's take a look at the reaction that occurs when acetic acid reacts with sodium bicarbonate, the reaction that occurs inside a volcano. In this reaction, if I were to place 5 moles of the acetic acid in 1 mole of the sodium bicarbonate, what would happen? Look at the equation. 1 mole of acetic acid reacts with 1 mole of sodium bicarbonate. In other words, a 1-to-1 ratio. So if I were to place 5 moles of acetic acid with 1 mole of sodium bicarbonate, only 1 mole of the acetic acid would have reacted. So there would still be 4 moles of acetic acid left in the reaction. Now let's think about this for a second. The reagent that is limiting the amount of products being produced is the sodium bicarbonate. This is what can be referred to as the limiting reagent. On the other hand, we have 4 moles of extra or excess acetic acid left. This is what is referred to as the excess reagent.
Now, another way to explain the concept of limiting and excess reagents is by using a cooking analogy. Imagine you're making a dozen brownies for a student in your chemistry class. It's his birthday. There are 24 students in the class, each of which you would like to make a nice brownie for. So you want 24 brownies. Each big brownie requires 1 egg and 1 teaspoon of sugar. So what you need is as follows. 24 eggs plus 24 teaspoons of sugar will give you 24 brownies. However, there were only a dozen eggs at the store, so you buy the 12s and 24 teaspoons of sugar because you're dumber than a dog. When you get home and get baking for the birthday boy, you realize that you were only able to make 12 brownies because you only had 12 eggs. You were left with 12 teaspoons of sugar, the other 12 being used up by the 12 eggs. In this case, there is excess sugar remaining, known as the excess reagent. The full potential of the sugar could have been used if there were enough eggs. The eggs were limiting the amount of brownies that could be baked for the birthday boy, so then we refer to it as the limiting reagent.
Now, let's move on from analogies to real chemistry equations. Let's look at the equation to form sulfur hexafluoride. Sulfur must react with fluorine gas in order to produce sulfur hexafluoride. To balance the equation, we must put a coefficient of 3 in front of the fluorine gas. This equation, in the end, tells us that 1 mole of sulfur will react with 3 moles of fluorine gas to produce 1 mole of sulfur hexafluoride. Now suppose that 4 moles of sulfur are added to 20 moles of fluorine gas. From the balance equation, we can tell that but there are 20 moles of fluorine gas available, more than what is needed to completely react with sulfur. Thus, the sulfur must be the limiting reagent, and fluorine gas must be the excess reagent. The amount of sulfur hexafluoride that can be produced depends only on how much sulfur was originally present.
So now we're going to be looking at another reaction. Say we have the following reaction. Ammonia plus hydrochloric acid, and the product of this reaction is ammonium chloride. So we're given 1 gram of ammonia and 1 gram of hydrochloric acid. Now we have to find out what's the limiting reagent, what is the excess reagent, how much of the excess reagent is left over, and finally, how much ammonium chloride was produced. Step 1 is determining the number of moles of each reagent. Since we can't tell by inspection which of the 2 reactants is a limiting reagent, we have to proceed by first converting their masses into number of moles. So we take each reactant and divide the mass of the reactant, which is 1 gram, by their molar mass, and we determine that there are 0.0587 moles of NH3 available, and only 0.0274 moles of HCl available. Step 2 is finding the limiting reagent. From the balance equation, we can see that 1 mole of NH3 reacts with 1 mole of HCl, Therefore, 0.0274 moles of HCl will react with 0.0274 moles of NH3. Hence, there will be some leftover NH3, and this will be called the excess. Since there's no leftover HCl, we can now determine that the limiting reagent is the HCl, while the excess reagent is the NH3. Step 3 is figuring out how much of the excess reagent is left over. We know that NH3 is the excess reagent, so all we need to do is subtract the number of moles used up in the reaction from the total number of moles. So we do 0.0587 moles minus 0.0274 moles, and we get 0.0313 moles of excess NH3. The final step is to find the amount of product of ammonium chloride that was produced. So here we just make a multiple ratio between the hydrochloric acid, which is the limiting reagent, and the product, which is ammonium chloride. So since the coefficients are both 1, it's a simple multiple ratio, so we can determine that 0.027 moles of the product, and then we just multiply the molar mass, and we get 1.47 grams of the final product of ammonium chloride.
Our next example will be a little bit more complex. Let's say you have nitric oxide, and it reacts instantly with oxygen gas to give you nitrogen dioxide. First, you'd want to balance the equation by putting a 2 in front of the nitric oxide and a 2 in front of the nitrogen dioxide. Next, since we're given the moles of each of the reactants, we have to divide the number of moles of each by their coefficients, which would give us 0.443 moles of nitric oxide and 0.503 moles of oxygen gas. This means that nitric oxide is the limiting reagent and oxygen gas is the excess. Since nitric oxide is the limiting reagent, we have to do a multiple ratio with nitric oxide and nitrogen dioxide, which means that 0.886 moles of nitrogen dioxide will be produced. Since you have 0.886 moles of nitrogen dioxide, you can easily find the mass by multiplying it by the molar mass of nitrogen dioxide. Next, we want to find the mass of the excess reagent remaining, which is oxygen gas. To do that, we have to do a multiple ratio between nitric oxide and oxygen gas. We would divide 0.886 moles of nitric oxide by 2 to get us 0.443 moles of oxygen gas used. Since we started with 0.503 moles of oxygen gas, we subtract 0.503 moles from 0.443 moles to give us 0.06 moles of the excess remaining. And once we have the moles, we can just multiply it by the molar mass of oxygen, and it'll get us the mass of the excess produced.
The number of moles of nitrogen dioxide that we just calculated is actually the theoretical yield of the reaction. If we were to perform this reaction, we would actually get the experimental yield. Experimental yield is the quantity of product produced in reality. In order to calculate percent yield, we take the experimental yield and divide it by the theoretical yield. After doing this, we multiply by 100 and we get a percent, which is our percent yield. Say we go to a lab and perform this reaction. We end up with 0.786 moles of experimental yield. We divide this by 0.886 moles, which is the theoretical yield. After that, we multiply by 100 and we end up with 88.7%. Therefore, the percent yield of this reaction is 88.7%. Now, our experimental yield is actually lower than a theoretical yield. Why is that? It's because of error. What if we want to find our percent error? Well, we take the theoretical yield, subtract the experimental yield from it, and then divide by the theoretical yield. Afterwards, we multiply by 100 and we get our percent error. So for this reaction, we would do 0.886 minus 0.786 divided by 0.886 and then multiply by 100, and we get a percent error of 11.3%.
In this lesson of Paul Academy, we talked about what are limiting and excess reagents, how to determine limiting and excess reagents when you're given chemical equations and the quantities of each of the reactants, and we learned how to perform calculations with limiting and excess reagents. We also learned how to calculate percent yield.
Thank you for watching this week's video on Paul Academy. Next week, join us to learn about solution chemistry and factors affecting solubility.